In the last section of Chapter 1, that's Section 1.10, we will study mathematical modeling and variation. All right, so mathematical modeling is important. It allows us to take real-life scenarios and make predictions or figure out different information based on some given quantities. All right, functions can be used as models to represent a wide variety of real-life data sets. For example, population of the US in millions from 2000 to 2007 are shown in the data table. All right, so notice for the year, and here we have our population. And over time, that population seems to increase. We can create a scatter plot of the data and allows us to see a relationship from year to year. Looking at the plot, it looks like it's almost a linear relationship. All right, and we can do something that's called run a linear regression that can be used to calculate the line of best fit. All right, if you take a stats class in the future, you will be doing a lot of best fit curves. All right, in this case, running a linear regression, which you can do on your calculator, we get y equals 2.78x plus 282.5. So having models like this can help us in predicting future values of our population of the US. All right, and so that's why it's neat to be able to kind of come up with some different relationships and models. In this class, we're not going to be doing regressions, okay? But we will be studying a couple different types of variation to see relationships between different variables. Let's talk about our first one here, direct variation. The most simple form of a linear model is y equals kx. All right, this means that the variable y varies directly as the variable x, or y is directly proportional to x, where k is a non-zero constant known as the constant of variation or constant of proportionality. Okay, you might notice that this is a linear relationship, and k, the constant of proportionality, actually gives you the slope of that line. All right, so this is known as direct variation, y equals k times x. So when we are trying to come up with our models, we're going to be given certain pieces of information, and those pieces of information will allow us to solve for this constant k. And once we have that constant k, we have an equation that will allow us to plug in other values and determine what our outputs will be. So, for example, the distance sound travels varies directly as the time that it travels. It takes 4 seconds for sound to travel 1,340 meters. Find a mathematical model that gives the distance sound travels as a function of time. All right. Now, in all of these problems, it's going to be important to identify your variables. All right. Variables are things that are changing. And so what's changing in this? Well, distance is one of those things that is changing. All right. So let's pick a letter that's going to represent our distance. I would choose the letter D. And the other thing that is varying is our time. All right. Let's use the letter T to represent time. All right. The distance varies directly. All right, think about this relationship. Y varies directly as x. We can take this expression and write the exact same thing just using our new variables. D is equal to k times t. Right? This is the exact same relationship. We have direct variation. We are just replacing it with our variables that we're using, which pick letters that makes sense to you, all right? Something that you're not going to get confused with another variable. That's why we chose D for distance and T for time, okay? So let's look at the given information. We know that when T is 4 seconds, D is 1340 meters. So we can plug in that information. Plugging in that information allows us to solve for K. To solve for K, I would divide by 4, and we get K is equal to 335. Once we have that constant K, and remember, a constant is something that is not going to change, all right? K is always going to be 335 in this equation, in this model. That means D is equal to 335t. Now that we have the model set up, we could find the distance that sound travels for any amount of time. Notice if we wanted to find the distance it would travel for after 1 second, we would plug in 1 for t. If we wanted to find the distance that the sound traveled after 10 seconds, we would plug in 10 for t. right? So determining this relationship gives us a lot of information, all right? We can figure out different distances for different amounts of time, right? So that's what we're going to be doing a lot of in this chapter, is coming up with mathematical models. Let's try another one. Hooke's law states that the distance a vertical spring stretches varies directly as the weight placed on the end of a spring. A weight of 80 pounds stretches a spring 6 inches. How far will a weight of 100 pounds stretch the spring? Okay, so again, the first thing we need to do is come up with a model that gives the distance the spring stretches as a function of the amount of weight that is placed on the end of the spring. Identify your variables. What are the things that are changing in this problem? 1, the distance the spring is stretched. That's our dependent variable, okay? And the distance the spring is stretched depends on the weight that we put on the end of the spring, all right? So we have D for distance, and I have chosen W for weight. Now, we know that the distance varies directly as the weight. Remember, direct variation, y equals k times x. Well, in this case, d varies directly as w. That would be d equals k times w. So we have our general expression here. In order to come up with our model, we must solve for this constant k. That is going to require us to plug in some given information. We know that a weight of 80 pounds will stretch the spring 6 inches. Plugging in 80 for W and 6 for D will allow us to solve for K. Here we get K is equal to 0.075. Once we have solved for that constant of variation, we can come up with our mathematical model. D is equal to 0.075 W. Again, that's just D equals KW. We found K, so we plug it in. This model will give us the distance that the spring stretches for any amount of weight. And so what do we need to plug in for our weight now? Well, we want to know the distance the spring stretches for a 100-pound weight. So we plug in 100 for W. D is equal to 0.075 times 100. That gives us 7.5 inches. One thing to keep in mind here, guys, because these are word problems, you will want to make sure that you are including units with your answer. Okay, include units with your answer. Another type of direct variation relates one variable to a power of another variable. This means that the variable y varies directly as the nth power of the variable x, or is directly proportional to the nth power of x. Now, this is not going to be a linear relationship, but rather some sort of power relationship, all right? Some sort of power function. Direct variation as an nth power that can be modeled as y equals kx raised to the n, all right? So it's similar. Again, we have direct variation. Whenever you hear the word direct variation, you are going to think about taking your constant of proportionality and multiplying it by your next variable, all right? So keep that in mind. All right, let's see if we can't do an example here. The distance an object falls from rest varies directly as the square of the time that it has been falling. So again, in these cases, we need to read the problems very carefully. And if it helps you, underline keywords. Notice that this says the square of the time. This tells us that our power n is going to be 2. An object falls 64 feet in 2 seconds. Find a mathematical model that gives the distance an object falls as a function of time. So again, when coming up with our models, the first thing we want to do, identify the variables. What is changing in this problem? Well, our dependent variable is the distance that the object is falling. All right, and the distance that it falls depends on the time t that it has been in the air for. Okay? All right, so we identify our variables, give them letter names that are representative of what they're talking about, right? Does it have to be D and T? Not necessarily, but pick letters that make sense to you. Now that we have our variables, we can come up with our mathematical model. All right, The distance varies directly as the square of the time. This would be y varies directly as x to the nth power. In this particular problem, we are going to have d, distance varies directly as the square of the time. D equals kt squared. Well, again, in all of these, our next step is going to be to solve for that constant of variation k. To do that, we need to plug in the given information. We know that the object falls 64 feet when t equals 2 seconds. 64 is equal to k times 2 squared. Solving for k, that would be 2 squared is 4. I'd have to divide 64 divided by 4, which gives me 16. Now that we have our constant of proportionality, we can plug that into our equation to get our model. D is equal to 16t squared. This equation right here, this mathematical model, will give us the distance that the object has fallen for any time value that we want to plug in. Let's do another example here. The range of a projectile is directly proportional to the square of its velocity. Again, read carefully. Range is directly proportional to the square of its velocity. When we see square, that's going to tell us we are talking about a power, and the power is going to be 2, right? That's what it means to square something. If a motorcyclist can make a jump of 140 feet by coming off a ramp at 60 miles per hour, with what velocity would the motorcyclist have to leave the same ramp to jump 200 feet? Well, let's start off by finding our mathematical model that gives the range of the motorcyclist as a function of the square of their velocity. Again, identify your different variables. What's changing? The range, how far the motorcyclist is jumping, let's call that R, depends on V, the velocity at which the motorcyclist leaves the ramp. And hopefully that makes sense, right? If the motorcyclist is going faster off the ramp, then they're going to be able to jump a greater distance. Let's now begin to set up our model. We know that range is directly proportional, varies directly to the square of its velocity. That would mean R is equal to k times v squared. Now we must solve for our constant of proportionality, k. In order to do that, we plug in our given information. We know that our range is 140 feet when we leave the ramp at 60 miles per hour. 140 is equal to k times 60 squared. All right, now we must solve for k. Solving for k gives us 140 divided by 60 squared. All right, that gives us k is equal to 7 divided by 180. Here's a pro tip when you guys are using your calculator. After you do 140 divided by 60 squared, you're going to get kind of a nasty looking decimal. Rather than rounding your decimal, see if it is possible to get a nice fraction by selecting Math and Frac on your TI-84. All right, use the Math Frac feature, and it gives us this nice fraction, 7 over 180. And so we get the range is equal to 7 over 180 v squared. Here is our model, right? So this is going to tell us how far we will be able to jump based off of the velocity at which we leave the ramp. So let's answer the next part of the question. It says, find with what velocity would the motorcyclist have to leave the ramp to jump 200 feet? So in this case, we're actually given the range R, and we are trying to find V. That's perfectly fine. Plug in the range in question to determine the velocity that is necessary to leave the ramp. There's our relationship. We plug in 200 for R. 200 is equal to 7 divided by 180. Well, doing out our algebra, we have 36,000 divided by 7 is equal to v squared. And taking the square root of that, we get v is approximately 72 miles per hour. All right, that is the speed at which we want to leave the ramp to ensure that we land safely on the other side. So there we have direct variation and direct variation as an nth power. In the next video, you'll see us talk about another type of variation known as inverse variation.